Okay, this is 3.3, and let's continue talking about operations on sets. So first operation is union. So union means S1 union S2. So this symbol, it looks like U, right? It means union, right? S1 union S2 equals to X such that X is in S1 or X is in S2. So for example, S1 is 1, 3, 5, and 6. And S2 is 2, 4, and 6. Right? There are two sets. So S1 union S2 should contain all the elements in both S1 and S2. Right, sorry. All the elements that's either in S1 or in S2. Right. So here in the example, it should be 1, 2, 3, 4, 5, and 6. Right, because the elements should be in S1 or in S2. Right. It doesn't matter if we include it in one of them or both of them. Right. As long as there's a one element that contain in any one of them, then you should be included in the union. Right. So let's draw a graph. The union should look like something like this. So we have this is S1, this is S2, and union is a collection of everything here. So everything here, right? Okay, this is S2. Right? So it should be the union, or all the elements in S1 and S2 should be included in the union part. Okay, so this example here. And the second one is called intersection. Intersection means S1, intersect S2. So it's opposite of U, right? The U, but it's open to the down, right? It's kind of like N, or it's a downward pointing U, right? So S1 intersect S2 equals to all the X such that X is in S1 and X is in S2, right? So the intersection contains the X, but X should be included in both S1 and S2, right? So it's a stricter condition. So let's give you an example. S1, 1, 1, 3, 5, 6 again, and S2 is 2, 4, 6, the same example as above. So S1 intersect S2. So let's write it again. So intersect should be the U, but it's pointing downward, right? Intersect S2. So pay attention to the difference between the intersection here and the union here, right? So the difference. So one, we can think of that union, it begins with U, right? So the symbol is a U. An intersection is different from union, so it's a downward U, right? Upside down. So S1 intersect S2 should be in X, so the element should be in both S1 and S2. And we can see that only the element 6 is in S1 and element 6 is in S2, right? So 6 is the only one common element in S1 and S2. So S1 intersect S2 should be 6, right? The only common element here, right? So intersection means finding the common elements in the two sets, and union means finding all the elements that in either set, right? And for the second example, S1 is 1 and 2, and S2 is 4 and 5. We can see that there are no common elements at all, right, for S1 and S2. So in this case, we say that S1 intersect S2 is the empty set, right? Because there's no element in common, so the intersection should be empty, right? So we use the empty set here to represent that there's no common element here. So here are the two examples. And the third type is called complement. Complement, I use S tilde to represent the complement of S. So S tilde is Sx such that X is a universal set and X is not in S. Oh, sorry, I forgot to draw the graph of intersection. So intersection should be something like this. So let's draw a little bit bigger. S1, S2, this is S1, this is S2. So intersection is in the middle. Right, so this is the intersection in the middle part, which contains in both S1 and S2. So if S1 and S2 are disjoint like this, right? So there's no in the middle part, right? There's no middle part. There's no common elements. So in this case, the intersection is empty. It's empty. Okay, so complement. First, we need to give you a definition of a universal set. So definition, universal set includes everything under consideration. So for example, I said U is 1 to 8. 1, 2, 3, 4, 5, 6, 7, 8. So that means that in this case, or in this example, or in this problem, we only consider the set U here, right? We don't consider the whole real system, or we don't consider all the other integers. The universal set, that everything that we consider in this example is just from 1 to 8, right? This is our scope of the problem we are talking about. So in this setting, for example, S is 3, 4, 8, right? Then S tilde, or the complement of S, should be everything that's included in the universal set, but is not included in S, right? The complement of the S. So in this case, it should be 1, 2, 5, 6, and 7. Right, together, S union S tilde is the universal set, as you can see. Right, S and S tilde are complement of each other. Right, but the universal set is everything that we just considered in this example. So if we draw a graph, it looks like this. So this is a U, right? The universal. The square, the rectangular is a universal set. It's the scope of the problem. We'll just consider the set here. And if I give you S here, then S2 that is everything that's in this universal set, but it's not the S here. So it's everything here, right, in the red shaded area. It doesn't include S, but includes everything inside this universal set. And the red shaded area is called the complement of S under the universal set U. Okay. Okay, so we just talked about the three operations. So this 3.3 and then 3.4, we'll talk about laws of set operations. Some laws, right? First, commutative law. Right, commutative law. So just like the numerical algebra you have learned, right? So commutative law, for example, A union B, something easy to understand, equals to B union A. As I said, union is just consider all the elements in S1 and S2, right? So whether or not it's S1 union S2 or S2 union S1, it doesn't matter, right? Because the elements here contain all the elements in S1 and all the elements in S2. They gather them together, right, into a union set. So A union B is just a B union A. And A intersect B is also B intersect A, right? Because based on the graph, whether or not S1 intersect S2 or S2 intersect S1 doesn't matter because we only want to find the common elements here, right? So the order doesn't matter. So this is a commutative law for the union and intersection. And second, associative law. So this is a little bit complex. So A union B union C equals to A union B and then union C. And A intersect B intersect C equals to A intersect B, then intersect C. Right? Because with B union C and the union A, well, it doesn't matter, right? Because we said that B union C or C union B doesn't matter. So you just want to find all the elements in A or B or C, right? And then gather them together. So whether or not you calculate B union C first or A union B first, it doesn't matter, right? Because the results are the same, right? Because both the operations here are union. And union means you just want to find all the elements in all the sets and then gather them together, right? So the order doesn't matter here. And for the intersection, again, intersection means you want to, so this equation means you want to find the intersection of A and B and C, right? So whether or not you first find the intersection of B and C, or you first find the intersection of A and B, it doesn't matter because the results are the same, right? As long as the two operations here are both intersection. So this is called associative law. You can calculate any one of them you like. Right? And the third one, we call this distributive law. So this is A union B intersects C. So the two operations are different from each other, right? This is union and this is intersect. So it's different from the first one, from the associative law. So this is A union B and the intersect A union C. And also A intersect B union C equals to A intersect B, the union A intersect C. Right. So it's kind of like when you learn in your high school maybe. So this distributive law you learn is something like this, right? A times B plus C, the summation of B plus C equals to A times B plus A times C. Right? So this is the distributive law that you learned before. But here in the set is something like this, right? Something like this, but with a different operation, right? So here it's hard to prove that, so we use an example to show why this is true. Okay. Right. All right. I'll write again. Sorry. I read again. A B C equals. Okay, so let me give you an example. If A is 4, 5, and B is 3, 6, 7, C is 2, 3, right? If this is the case, and first let's calculate A union B intersect C. So this is A is 4 and 5, right? Union. So what's B intersect C? So B intersect C means we want to find a common element in both B and C, right? So the only common element here is 3, right? 3 in B and C. So this is 3 here. And for the union, we want to find, we want to gather all the elements in both sets, right? So here, the union should be 3, 4, and 5. And let's calculate A union B, and then intersect A union C. So A union B should be all the elements here. So 3, 4, 5, 6, 7, right? Because union means we want to gather all the elements in both sets. So 3, 4, 5, 6, 7. And then intersect with A union C, 4, 5, union 2, 3, right? So they should be 2, 3, 4, and 5, right? All the elements. And then we want to find the intersection of these two sets. That means we want to find a common element here, right? So we have 3 common elements, and they are 3, 4, and 5 in both the set here. So we can see that these two are equal. The results are equal to each other, right? The results are equal to each other. And then we can calculate the second one. A intersect B union C. So what's this? This should be A is 4 and 5. Intersect B union C should be 2, 3, 6, and 7, right? So the intersection is empty because there's no common element in these two sets. So the result should be empty. And also A intersect B, and then union A intersect C. So this should be, so first A intersect B is also empty, right? Because 4, 5, and 3, 6, 7, there are no common element here. And the second one, union, A intersect C, should also be empty, right? Because 4, 5, and 2, 3, they have no common element, no common elements. And empty set union, another empty set, is still an empty set, right? Because all the elements here are empty, and so whether or not you union or not is still an empty set. So these two things are also equal to each other. Okay. So this is a distributive law, and we talk about the three things here. And we're done with the sets. So for the last part of the review, we've done with the sets, and then we talk about something about functions. Functions. So first, let's talk about ordered pairs. Okay, ordered pairs. Ordered pairs mean order does matter. Right? In the set, we say that whether or not it's 4, 5 or 5, 4, it doesn't matter because the order doesn't matter, right? It just means there are two elements here. One is 4, one is 5. But who is ahead of whom, it doesn't matter, right? So this is set. But for the functions, the order does matter. And we don't use a curly bracket to represent a function, or sorry, to represent an ordered pair, but we use just a common bracket here, AB, to represent an ordered pair, right? It says pair, so there are only two numbers here, A and B. Right, A and B could be any number, right? I just use AB to represent a parameter here. So the ordered pair AB is different from the ordered pair BA. Right, so for example, if we use A to represent the math score and use B to represent economic score, right? Then of course 90 and 85 is different from 85 and 90, right? Because they don't represent the same thing. 90 means your math score is 90 and 85 is your economic score. But if you reverse that, the 85 and 90 means one, the math is 85 and economics is 90, right? So that means A and B have different meanings, and so you cannot just interchange them, right? They do have order here. So this is called ordered pairs, right? For another example, I think you already know that this is an example of a rectangular or we also call this Cartesian coordinate plane. Right. I think you already know that, so this is a review. Sorry. So this is a rectangular plane, something like this. Right. This is x, this is y. So x means x axis and y axis. Right. So this is a coordinate plane. And in this plane, we can draw the infinite set of ordered pairs. Actually, we can draw all kinds of ordered pairs in this plane, right? So you can think of x as the A and y as the B, right? But just represented by different things, right? But A, B, or x, y is just the same, right? A different name of a same parameter, right? You can think of x as the A here, the 90 here, and the y as 85 here. Anyway, so for the x-axis, to the right, they are positive. To the left, the negative number, right? And it has the same interval here. So 1, 2, 3, and so on, and -1, -2, -3, and so on. So y here is 1, 2, 3, right? The up part, the down part is -1, -2, and -3, right? So we use this system to, we can draw all the ordered pairs in this graph. So for example, what if I draw 1 and 2 here? So 1, 2 means x is 1 and y is 2, right? So this is the ordered pair. So x is 1, we first find 1 here, and then y is 2, and then we find 2 here, and then we draw a point on the plane. So this little point means this point has a coordinate 1 and 2, right? And if we want to draw 2, 1, as I said, 1, 2 is different from 2, 1 because they're ordered pairs. So that can be represented in a plane here. Again, x is 2, y is 1. I see that this coordinate is different from this coordinate. 2, 1 is something here. First, we find the 2 on the x, and then we find 1 on the y. So here, this is 2, 1, right? But this is 1, 2. So this point is 2, 1 here. It's different from 1, 2, right? So we can see that all the ordered pairs can be drawn in this graph, in this coordinate plane, right? So this is also called Cartesian plane. Okay, and then we talk about function. So 4.1 is the background, and then we talk about functions. Okay, definition. For each x value, there exists only one corresponding y value. Then y is a function of x. This is a definition of function, and we can denote this by y equals to f of x.